This video will accompany the Chapter 5 notes. Notice for Chapter 5, we're only covering parts of Section 1 and Section 2 from the book. Chapter 5, Probability in Our Daily Lives. Before collecting the sample, we do not know what the value of the statistic will be, but we may be able to predict what will happen. We say the statistic is random since we do not know the value before collecting the sample. We need to learn about probability, which is also known as the science of uncertainty. Section 5.1, How Probability Quantifies Randomness. Definition. We will measure the chances of the possible outcomes for random phenomenon, everyday situations for which the outcome is uncertain. Remember the randomness of assigning subjects to treatments in earlier chapters. With a small number of observations, random phenomena may be look very different than what you expect. However, with a large number of observations, things settle down and we start to see what we expect. A process is random if the outcome of the process is unknown before it occurs, but the possible outcomes follow a regular pattern in the long run. For example, consider rolling a fair die. Before throwing the die, you do not know where it will land, but you do know there is a 1 in 6 chance of seeing any particular face if it is a fair die. We have a die and want to know if it is fair. We can see the results for our example experiment below. So notice, looking at the left column, we have different trials. Each of these trials mean that we rolled the die. So we rolled the die 100 times. This column gives us the dice results for each of the 100 rolls. This column tells us yes or no, did we see a 6 on that particular outcome. Here, we're looking at the cumulative proportion. So as we go through, we're counting the number of times that we see a 6 and dividing by the number of rolls, so on. So looking here, notice that the denominator for each of these fractions is the same as the trial, because each trial number tells us cumulatively how many times we have rolled the dice. The numerator only increases by 1 each time that we roll a 6. So coming down to the bottom, we see that we rolled a 6 23 out of the 100 rolls. A trial is any procedure that can be repeated infinitely and has a well-defined sample space, which is a set of all possible outcomes. In this example, each roll of the dice is considered to be a trial. And again, the number of these trials are located here. After each trial, we record whether a 6 occurred. Again, this is this column. A running record of the proportion of times that a 6 occurred is kept, and each value for the number of trials, and this is called the cumulative proportion, again, given in the last column. Here we have a plot where the 6-sided dice was rolled 100 times, and over time the proportion of times the dice landed on a 6 was updated with each roll. If the dice was fair, would the results be unusual? And that's the question we're going to try to answer here. So notice that if the dice were fair, we would expect there to be a 1 out of 6, every 1 out of 6 rolls would land on the 6. This line right here represents 1 divided by 6. Notice over time that the actual cumulative proportion that we saw is getting closer and closer to the line that we would expect. And so the question is, over time, will it get even closer, suggesting that this is a fair coin, or will it just stay above, suggesting that it may not be a fair coin? Probability quantifies long-run randomness. In 1689, mathematician Jacob Bernoulli proved that as the number of trials increased, the proportion of occurrences of any given outcome approaches a particular number in the long run. Bernoulli's result is called the law of large numbers. Note, this only applies to the long run. In the short run, things can be quite different. Just because you've gotten a particular result does not mean that the universe owes you a different outcome on the next trial. So we have 2 more definitions here. The probability of a particular outcome is the proportion of times that the outcome would occur in a long run of observations. Different trials of a random phenomena are independent if the outcome of any one trial is not affected by the outcome of any other trial. Bayesian statistics. In some situations, you may assess the probability of an outcome by taking into account all of the information you have. So you're relying on subjective information rather than solely on objective information such as data. In this subjective definition of probability, the probability of an outcome will occur based on the available information. Bayesian statistics, in honor of Thomas Bayes, uses subjective probability as its foundation. We will not be using this definition in our course. We will be using data and traditional probabilities, but this is an interesting side fact. Section 5.2, Finding Probabilities. A process is random if the outcome of the process is unknown before it occurs, but the possible outcomes follow a regular pattern in the long run. For example, again consider rolling the die. Before rolling the die, you do not know where it will land, but you do know there is a 1/6 of landing and seeing a particular face if it is a fair die. The sample space of a random process is the set of all possible outcomes. It is denoted by capital letter S. For the dice example, notice that our sample space is S is equal to, we use curly brackets around the potential outcomes, and then listed inside of the curly brackets, we have the 6 possible faces that the dice could land on. An event is an outcome or set of outcomes of a random process. We denote events with a capital letter, with the exception of the capital letter S, since it is reserved for sample space. For example, the event that a die lands on an even face can be denoted by the following. So here we've used the capital letter A to denote the event, and again we're going to use curly brackets, and inside the curly brackets to say what outcomes denote that event. So we could say the die lands on an even face, which would be the outcomes 2, 4, and 6. The probability of an event is the proportion of times that the event would occur over time. Probabilities are always between 0 and 1. For example, if we roll a die an infinite number of times, I expect the die to land on the number 3 1/6 of the time. We would write, and notice here we've got a capital P and then parentheses. And then inside the parentheses, dice lands on 3. The capital P here stands for probability. Inside the parentheses, we have what we're interested in finding the probability of. So this would read, the probability that the die lands on a 3 is equal to 1/6. A probability model assigns a probability to each outcome in the sample space and describes how to calculate probabilities of events. Let's look at an example and look at each of the definitions for this example. So again, we're going to consider rolling a dice, but this time we're going to roll 2 fair dice and observe the sum of the dots on the pair. The possible outcomes are depicted in this picture. So the first thing we're going to do is identify our sample space. So notice here, since we're interested in the possible sums of all dots on the pair, the sample space is as follows. We could see a sum of 2, 3, 4, all the way up to 12. Also notice that we only write each of the numbers 1 time. Next, we're going to write out the probability model. We do this by first writing down the sample space. Then for each element in the sample space, we're going to find the probability of observing that sum. So let's start with a sum of 2. Pardon me, I should have said let's start with a sum of 4. So the question is, what is the probability that the sum of the 2 dice is equal to 4? Well, we can look back at our diagram. Notice that there are 3 different possibilities that would result in a sum of 4. Also notice that there are 36 different pairs for how the 2 dice could land. This gives us the probability of observing a sum of 4 equal to 3 divided by 36. Pause the video here, and when you come back, we will look at this filled in, but see if you can fill in all the probabilities. Were you able to find these values? One thing to notice here is that if you add up all of the probabilities, they do sum to 1, and this should happen anytime you build a probability model. See if you can answer the following. List the sample space for each of these. Pause the video, and when you come back, we'll look at the answers together. For the first one, we're going to roll a 13-sided die one time. Notice we're going to use the capital S to denote the sample space, equals, and then in between the curly brackets, we have all of the possible outcomes. Well, if we roll a 13-sided die one time, the possible outcomes are the numbers 1 through 13. We're going to flip a fair coin once. Again, we have capital S equals curly brackets, and inside the curly brackets, we have the different potential outcomes. Well, for a coin, we could either see a heads or a tails, so our sample space is head-tail. And then finally, if we're going to flip a fair coin 3 times, notice here we have the 8 different ways the coin can land each of the 3 times. Let's continue our example where we considered rolling 2 fair dice and observing the sum of the dots on the pair. The possible outcomes were depicted on page 3 of your notes. We're going to look at the event A is equal that there are more than 10 dots on the pair of dice. Notice this is the same as saying that the sum is 11 or the sum is 12. We'd like to find the probability of the event. Well, again, we could look at our diagram of all of the possible ways that the 2 dice could land, and notice that the 3 in the bottom right-hand corner, all 3 of those pairs have the sum 11 or 12. Therefore, our probability is 3 out of the 36. We could also have used our probability model at the top of page 4 to find these probabilities well. Now it's your turn. Suppose you flip a fair coin 3 times. First, list the possible ways that you can get 2 tails and find the probability of this event. Pause the video, and when you come back, we'll look at the solutions. There was an error on the slide that I just fixed. Your notes say, list the 2 ways that you could get exactly 2 tails. I've added the word exactly to the slides. So let's look at the answer. List the ways that you could get exactly 2 tails. Well, notice these are the 3 different ways we could get exactly 2 tails. And since there are 8 possible outcomes, the probability of this event is 3 divided by 8. This brings us to the probability of an event. When all the possible outcomes are equally likely, the probability of an event, denoted probability of A, is obtained by taking the number of outcomes in an event A and dividing by the outcomes in the sample space. Notice there are 3 different properties that these probabilities will always have. The probability of each event is between 0 and 1. The total of all the probabilities in the sample space equals 1. And except for simplistic cases like flipping a coin or tossing a die, different outcomes are not usually equally likely. Next, we're going to look at Venn diagrams. We often use Venn diagrams to represent how events are related to each other. A Venn diagram uses a box or a rectangular square to represent the universe, or simply the sample space as a whole. Then ovals or circles are used to represent particular events. The complement of event, A, denoted A, superscript C, consists of all outcomes in the sample space that are not in A. Since the probabilities of A and A complement add to 1, we have the following. The probability of A complement equals 1 minus the probability of A. In a picture, here's what we're saying. If the box represents the entire sample space and the oval represents A, then A complement must be all of the things outside of A. Sometimes using the complement is an easier way to find the probability of at least one of several events will occur. It can be easier, instead of dealing with all of those separately, to simply find the complement, which is that none of these events will occur. Two events A and B are also said to be disjoint if they do not have any common outcomes. Here, we're going to look at a Venn diagram for disjoint sets. So here's an example where we have a Venn diagram showing two sets that are disjoint. Notice we have a circle for each of the events A and B, and they do not overlap. Pause the video and see if you can write a Venn diagram for three disjoint sets. Does your Venn diagram look something like this? We can also talk about the intersection and union of sets. The intersection of A and B consists of outcomes that are in both A and B. The union of A and B consists of outcomes that are in A or B or both. Notice in your notes the notation used for both the intersection and the union. Here are the corresponding Venn diagrams. Notice that the intersection only consists of the overlap, whereas the union consists of everything in A or in B. Consider this example. We have a sample space and we have several sets. Let's see if we can write some of the following in set notation. First, we're going to look at D complement. Notice that D is equal to 6, 7, 8, and 9. Therefore, D complement will be all of the elements of the sample space which are not in D, leaving with 0, 1, 2, 3, 4, and 5. We could look at A intersection B. A intersection B is all of the elements that are in both A and B. So looking at A and B, we can see the numbers they have in common are 0, 2, and 4. On the other hand, A union B is all of the numbers either in A or in B. So notice that each of the numbers in A union B is in A or B. For numbers that occur in both, such as 0, we only list that number once. Let's look at B intersection C. Notice that B and C do not have any numbers in common. Therefore, we say that that intersection is equal to the null set. You can see the notation for the null set here. We could look at C intersection D intersection E. This would be all of the numbers that all three of them have in common. Notice the only number that is in all three of the events is the number 7. So here, the intersection of C, D, and E is just the number 7. We could also look at the union of C, D, and E, and notice the union here is any number that occurs in at least one of the events. So here we have the union of all three. Here's another example. See if you can draw a Venn diagram for the following. Here is your sample space, and we're interested in the events G and H. Pause the video, see if you can construct each of the Venn diagrams, and when you come back, we'll look at the solution. To draw the Venn diagram, we're going to start by building a rectangle, which represents the sample space, and we're going to draw an oval for G and one for H. Notice looking at G and H do have some values in common, such as 0, 2, and 4, so we know that there is going to be some overlap between the two. So in the overlap, we're going to place the numbers 0, 2, and 4. Next, we're going to fill in the numbers that are in G, but not in H. So notice that the numbers 1, 3, and 5 are all in G, but not in H. And then we'll fill in the numbers that are in H, but not in G. Notice that 6 and 8 are not in G. We're almost finished. In the last step, remember that the square as a whole represents the sample space, and there are three elements in the sample space which are not in G or in H, and those are the numbers 7 and 9, so we will draw them outside of G and outside of H. Consider this example. Now we have three different events in the sample space. Pause the video and see if you can draw this Venn diagram, and when you come back, we'll look at the answer. For this example, you should have drawn your rectangle and 3 circles with overlap, and then filled in the numbers as so. Next, we'll talk about calculating probabilities. We have the addition rule, which is the probability of the union of 2 events. For the union of 2 events, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Notice that the events are disjoint, probability of A and B is equal to 0, so we just have the probability of A plus the probability of B. In an image here, what we're saying is if we took the probability of A, and we could look at the Venn diagram of A here, and add to it the probability of B, looking here at this Venn diagram, notice that the middle section gets counted twice. So that's why we have to subtract off the probability of A and B. We also have the multiplication rule. For the intersection of 2 independent events, and they must be independent, A and B, the probability of A and B is equal to the probability of A times the probability of B. Recall that independent means that what happens on one trial is not influenced by what happens on any other trial. Consider this example. For a 3-question multiple choice pop quiz, a student is completely unprepared and randomly guesses the answer to each question. Each question has 5 options. With guessing, the response on one question is not influenced by the response on another question. We are interested in the possible outcomes of the quiz, i.e., if the answer is right, denoted as R, or wrong, denoted as W. First, we're going to write the sample space for the possible outcomes of the quiz. So notice here, since the student is going to answer 3 questions, the student could get all 3 questions wrong, all 3 questions right, or some combination therein. So there are 8 possible outcomes. This is very similar to when we flip the coin 3 times. So next, we're going to find the probability of the possible student outcomes for the quiz. Since these events are independent of one another, we can use our multiplication rule. We know that they're independent because the student is just randomly guessing at each question, so it's not influenced by the response on another question. So notice here, for the probability of getting all 3 wrong, we would multiply the probability of randomly guessing wrong, for the probability of getting 3 right, I should have said. This is equal to the probability of getting a question right when randomly guessing, which is a 1/5 chance since each of the questions have 5 options, times that 1/5 chance times the 1/5 chance. Continuing, here are the rest of the outcomes and their corresponding probabilities. Next, we'd like to find the probability that the student gets at least 2 questions correct. Notice that each of these 4 outcomes represent that at least 2 of the questions are correct, so we can add up those probabilities to find an overall probability of approximately 10.4%. We have one more example. Based on records of automobile accidents in recent year, the Department of Highway Safety and Motor Vehicles in Florida reported that the counts who survived and dies according to whether they wore a seatbelt, yes or no. The data are presented in the contingency table below. For all answers in this problem, round each answer to the nearest thousandth. Take a moment and see if you can answer some of A through E. When you come back, we'll look at the answers together. First, we're going to look at the sample space. So notice here we have a representation of the possible outcomes for a randomly selected individual in the auto accident. Here, we have yes, they wore a seatbelt, and S for they survived, wore a seatbelt and died, no seatbelt survived, no seatbelt and died. We want to use these data to estimate the probability that a person dies and the probability that they didn't wear a seatbelt. So notice here we have a total of 2,111 people who died, 2,111 people who died, And we have 164,128 people who were not wearing their seatbelts, all out of a total of 577,006 people. Using these two values, we can find the corresponding probabilities. Next, we'll use the data to estimate the probability that an individual did not wear a seatbelt and they died. So notice the number of people who were not wearing their seatbelt and died was 1,601. So we can divide that number by the overall total to find that probability. Now, using the parts in B and C, we can determine whether the events of D and N, whether the events died and not wear a seatbelt are independent. So notice here, we already found the probability of D and the probability of N. Multiplying the two together gives us this value. Since that value and the value found in part C are different from one another, then these events are not independent. If they had been the same, then we could use our rules for independence to say that they were independent. In context of the data, what does this tell us? Well, it tells us, since these are not independent, that for those that were not wearing their seatbelt, whether or not they died was not independent of them not wearing their seatbelt. That concludes the Chapter 5 notes.